statistics, how to report them. Also choose the right slide back and report it. And here we go. Okay. And so as you can imagine, choosing the right statistics with this plethora of different tests that are available and the ease of use of statistics software to essentially employ them is quite challenging at times, and thereby tables like this and decision trees like that make it actually quite useful. So essentially you're looking at this. So decision trees are used in quite different contexts. They're often used in medical decision making and diagnostic pathways. So it is here to some extent. So you basically you're starting on the first level, and you have four use case scenarios. You have a scenario where you have one scale variable, then you have a nominal independent variable, so category, and a scale dependent variable. You have only nominal variables, and you have only ordinal variables. And we will get to that. Because also of note, you may not need to know how to do non-parametric tests, but Chapter 18 discusses them and gives you kind of a taste of these names, because you may not need to use the test, but you need to know about them. So first use case is where you only have scale variables, and this is what we did most recently. Chapter 15 and 16, we talked about correlation and regression. So when you have only scale variable and your dependent variable and the independent variable scale, you basically ask yourself, do you want to only look at association, or do you also want to predict it? If you want to test the association, you do the correlation coefficient. If you also want to predict it, you use the correlation coefficient to basically predict your standardized dependent variables set y hat by using your R to utilize multiplied with the standardized X, getting you actually possibility to then calculate the actual predicted y. So if you have a nominal independent variable and a scale dependent variable, that's really what we spend most time on this entire semester. So that's the scenario where you have either, so if you only have one independent variable and you have a scenario where you have two groups, so two levels of the independent variable, you go down that pathway where you either have a sample and a population, and you're comparing the sample statistic to population parameters. I'm flagging this right now. I'm explicitly for a reason saying it in that way. If you have a mean and a standard deviation of a sample, this is called a statistic. If you have a mean and a standard deviation, mu and the sigma from the population, this is called a parameter. Know that distinction, don't trip into that. Okay, one represented by a sample, one by the population, two groups, you're coming down, independent parameter, independent variables, two levels. If you have a sample and one is the population that you're comparing it to, or alternatively, any reference range of interest. You have a population standard deviation, and you have a sample statistic, and you're asked to compare the sample mean to a random reference value, the blood pressure of 120, for example, or I don't know, the average weight of fish in the Atlantic Ocean, but the standard deviation of your fish population is 18 grams. If any reference value that you're comparing your sample to basically can serve, it doesn't necessarily have to be a population parameter. So if you know your mu and your sigma, you can use a set test. Or alternatively, if your sample size exceeds 30, you can also use a set test. Remember that. If you only know the mu, you calculate your mean and you calculate your standard deviation. It's a different standard deviation. Now it's a standard deviation where you calculated the variance by dividing the sum of squares by the increase of freedom, not by the actual sample size, as we did for the population. So it's basically then an estimate of the population standard deviation by kind of manipulating your standard deviation calculation by using the degrees of freedom instead of the sample size, thereby lowering the magnitude of the denominator and kind of making the standard deviation wider. So that's this manipulation of the standard deviation estimate. Thereby, it's more likely to reflect the standard deviation in the population, aka sigma. If we do that, we're basically employing a single sample t-test for basically our thresholds for the critical t cutoff are changing with each degree of freedom. Keep in mind the t-score table, the z-score table, the t-score table, and f-score table, I-squared table, and an R table. Good. Okay. So one represented by a sample, one by the population, or any other reference value if mu and sigma are known, think of the z-test, or when the samples are greater than 30. If only the mu is known, think of the single sample t-test. If you have two samples, you need to ask yourself, yes.
What if the sample is greater than 30, but you don't know the standard deviation?
Then you're estimating it, but you can use
But you're still using a t-test.
correct, because now you can use the thresholds of c-test.
And you shouldn't use the t-test at all. Like it would be wrong to use.
Nah,
the
that's I wouldn't say it like that. You can get away with it.
Like answering a t-test would be the wrong answer.
It would not be the wrong answer, and it's not only about the answer. So in the end of the day, what you want to have, yeah, on a quiz, you do it either way. I give you the points. If Nolan and Heinzen doesn't agree with you, I would. So in the end of the day, that's what counts now for the family, right? But so the reason, so this 30 is a rule of thumb. And the reason is when you look at the t-score table, and this is, they get very close to that threshold. Exactly, that's 5%, that's 2.04. If you look at the z-score, you're basically at 1.96,
So
right?
you're saying like your result would be very similar.
And if you're different by like 0.08, this is not making a lot of a difference. So that's the rationale behind it. For the sake of simplicity, 30 was chosen as the threshold. Sure. So you're using an alpha of 5% on a SEP test or a t-test. So if you are looking your critical value up with a t-score of 30, let's take 30, the sample size of 30. You have a two-take t-test with an alpha of 5%. Your critical t would be 2.04.
With the with 30 being the two.
So that's your critical t. If your t estimate exceeds 2.04, you basically you are exceeding. If it's 2.05, your t is larger in the two-take test, and you basically you can see you have significantly rejected your null hypothesis.
Oh, that's the cutoff.
And the cutoff is if you have, let's say, 30 or 31, your cutoff could also be 1.96. It's not, you get away with it. It's not the proper way to do, but it is close enough. That's why out in the wild, it is basically kind of like you estimate the confidence intervals by taking 1.96. And that's usually when you use that. It's like in other cases, you don't do hypothesis testing at this point in time. You don't do hypothesis testing yourself by calculating a t-score. You run it in R, you run it in SPSS, you see a significant result, and that's how you interpret it, right? You have SPSS do the work for you, estimate an exact p-value using mathematical function, but you're not going to a t-score table. It's like I haven't, before I started teaching at Stern, I haven't seen one of this table in quite a while. So it's really more preparing you for what is coming your way. The only time when you do use it is when, for some purposes, you do some estimations in Excel, you calculate your own confidence interval. And then it's kind of useful that you know, okay, so now it's 30 is like now I calculate the CI using 1.96 rather than 2.04. So for this purpose, it comes then really as being interesting. Okay. Makes it clear?
Yeah.
All right. Okay, so back to chapter 18. So we have now, we have had now, two samples. So one sample set test and t-test, two samples we distinguish. Okay, so was each individual going through each level of the independent variable hours? Yeah, going through each level of the independent variable. If we have two samples and these samples are defined, the levels of the independent variable are defined as before and after the single pair sample t-test, or there are some chronological difference between them. So they were first doing that survey, then doing that survey. They were doing, I don't know, first yoga and then swimming. So some chronological difference, but it's the same individual. Then we think of a pair sample. The testing against the null hypothesis of the change between before and after equals 0. If there is an expected change, the null hypothesis becomes that expected change. So we are calculating the comparison distribution is here the difference from before to after. That's your comparison distribution. And that's also your degree of freedom. So it's the number of differences from before to after, which is identical with the sample size minus 1. So if you are testing now that difference, you're comparing that difference by division by the standard error of the mean, comparing this to your t-distribution of the differences. If you have an expected change, you need to subtract this change from your difference. And that becomes then your numerator in the division estimation of the. But just go back to the Excel spreadsheet, you will be able to remember the problem. So two samples between groups designed, that becomes independent sample test. The subtlety is that each individual is only in one level of the independent variable, not in both. That is important to keep in mind. What's also important to keep in mind is like you need to pool the variances. You have different variances in both groups. You need to pool those, and you need to pull them together to estimate the standard error of the mean and to compare the differences between the means. Remember, we have two different samples. We're pulling out little subsamples. We're building a mean. We're calculating the difference between those means. We're dropping the subsamples in. We just keep that difference. And then we build more and more of these differences, and then we have a distribution of the differences between those means. And that's our comparison distribution, which we again compare against the null hypothesis of 0, or alternatively, any anticipated difference between the groups. The next important subtle difference is that the degrees of freedom for your pooled variance is different than the one from the paired sample t-test. That degree of freedom is now both samples minus 1. That means it's entire sample size of group 1, group 2, added together minus 2. So you subtract 1 to get to your degree of freedom for each group. The same as you do with correlation and regression for that now. Keep that in mind. That's don't trip into that one. Good. So that's independent sample t-test. And it's a little bit more complicated to calculate, but there may be some simple calculations, but nothing terrible. Also, by the way, I've excluded now the source table examples from the ANOVA, so there will be no extensive calculations to be expected for fun. You're welcome.
With no Excel?
Hmm?
With no like full-on Excel calculation?
No, you will need to do some calculations, like you get a source table and give me the R, give me the S, give me the F. So interpret the source table, calculate F from MS1 to MS2. So there will be some simple calculations, but not. So there were a couple of questions in there, like you have that table, that table, that table, calculate the source table and complete the source table. So I did the exercise myself. It took me longer than 2 minutes, so I deleted those questions from the question banks. Yeah, you're welcome. It just made sense. Good. Yeah, it was not. Good. Independent sample t-test also be prepared to do some simple calculations, but not extensive. Simple. Okay, so you have one independent variable, you have three or more groups. We know this is an ANOVA. We know if it's three or more groups, within groups design and between groups design. Here, if the individual goes through each levels of the independent variable, then it's a within groups design. If it's between the groups, it's a between groups design. The difference, you basically calculating F by calculating the between groups variance. So the variability between the group means from the grand mean over the variance within the groups. So this relationship between these two variances basically allows you to get an estimate whether one group is different from one other group. Because the null hypothesis is that all three group means are equal. So the one way within groups ANOVA carries this to the next level because it subtracts the variability between the subjects from the equation. Because now you have this intersubject variability being contained and removed by basically reducing now the variance between the groups, not the variance within the groups, to only that variance that constitutes to the changes in the level of the independent variable and gives you the true estimate of variation caused by the actual levels of the independent variable. So it gives you a more accurate estimate of your F in the end of the day. So know those differences. So three or more groups, three or more levels is basically ANOVA. Good. Two or more independent variables, that gets you to factorial ANOVA or a two-way between groups ANOVA. Will not be part of the final. However, we'll need to know what it is. So you will need to understand that this is two different independent variables. And you're testing the interaction between these two by factoring in your factorial ANOVA. So just know what it is, know how to point at it, and know the concept of it, but you don't need to calculate it. Okay, if you have only nominal variables, and this is now the example that we did in chapter 17, so we have one nominal variable, that's the soccer players in Germany. So early in the year, born early in the year, and born late in the year. So the nominal variable with two levels is basically year, season of the year. So that's your nominal variable, and this basically you compare the percentages, or you compare the counts in these two levels. If you have two nominal variables, which now we're getting closer to the paper cup, where we have outcome variable, dependent variable was trash or recycling. Independent variable was three levels of independent variable was name on it correctly, name misspelled on the cup, or no name on it at all. If you're testing there for an association, you will find an association by the quantification of the chi-square in the chi-square test for independence. So test for goodness of fit versus test for independence. Know the difference. Okay, and now we're getting to that part which you don't need to know, but you will still need to know where to look it up. And I want you to have first the names of these tests, because they're quite common. If you have only ordinal variables, or alternatively, you have non-normally distributed variables, you would resort with two ordinal variables where you basically interested in association. You use a Spearman rank order correlation coefficient, the Spearman rank test. Spearman rank order correlation coefficients. In two sentences, what it does, it basically takes two variables, and we have with a correlation coefficient, the Pearson correlation coefficient, the standard correlation with it. You basically take the actual raw entries and the actual variables, and you're relating that association to each other, right? So you're calculating the sum of the products between the individual scores, the individual deviations, and you're dividing it by the sum of squares, the product, the sum of squares of x and sum of square of y. You're square rooting it, gets you your correlation coefficient. Now here you don't use the actual individual raw number, the actual value. Here you're basically ranking them. You're ranking them within that whole sample that you have, so highest to lowest, and the same as the second variable. And then you basically associate the ranks, because in that way, by confirming, by converting them into ranks, you don't need to deal with the distribution that is not normal. That's why it's here listed as ordinal. Good. Spearman rank order correlation coefficient, actually non-parametric testing. With beauty, it doesn't make any assumptions about the distribution. Okay, next, nominal independent variable, ordinal dependent variable. So you have now essentially a within groups design. So welcome. This is also, it would also be true for scale variables, where you basically make the same concept applies again. So you basically have a within groups design, you have a Wilcoxon signed rank test. Wilcoxon is essentially the non-parametric brother of the paired sample t-test. So you can use it in the same format. Then you have nominal independent, ordinal dependent variable. You have between groups design, which is two groups. It's the Mann-Whitney U-test. Mann-Whitney U-test is the non-parametric brother of the independent sample t-test. And last but not least, three or more groups. So three or more levels of independent variable gets you the Kruskal-Wallis H-test, non-parametric brother of the ANOVA. So that's the non-parametric scheme. So that's new, but you just need to know how to read that decision tree. And please memorize the names of the test. There's a good chance they will come your way. If you do, but particularly if you go in the realm of psychology, it's quite common to use non-parametric tests. All right, any questions on this decision tree? I think it's quite simple, right? So I'm just flagging this. That's going to be very useful. I would almost like print it and have it next to me. Okay, so we talked about this. Good. We talked about it. I don't think there's much value to go through the table again. Goodness of fit, we talked about it. Soccer players early in the year, late in the year. It's one nominal variable. If you have two or more nominal variables for dependent and independent, use a chi-squared for independence. You're testing with a chi-squared. You test for an association between the dependent and the independent variable. Your null hypothesis is that these are not related to each other, not associated with each other. The alternative hypothesis is that there is an association. You're quantifying the chi-squared by basically calculating the square root of the sum of all observed minus expected differences squared divided by the expected counts. So doing this gives you chi-squared. The chi-squared basically allows you to then test against the comparison distribution, which is a chi-squared distribution, which is unimodal and right-skewed, dependent on the degrees of freedom. And if it exceeds a critical threshold, you basically are rejecting the null hypothesis of there being no association. You can test the effect size with grammars V or phi. You can, in addition, calculate adjusted residuals, adjusted to standardized residuals, which allows you to do further post hoc testing. You can also quantify relative risk if you're interested in actual risk increases or actual probability increases when comparing those groups. And we did that with the paper cup. Relative risk, I would very much recommend to kind of keep in memory, because it's quite central to a lot of disciplines. What's important to keep in mind is, this is more an FYI, and this is a take-home message for you, because you will, in your further education, you will be, bless you, exposed to writing papers, writing scientific papers, writing thesis. I don't know where you're going with your education, but there's a good chance if you stay somewhere in the realm of medicine, psychology, you will report some statistics. So there are resources for the psychologists here, resources that allow you to basically see how to report your statistics. So I don't know Marianne Fallon's article, but there are various articles. The British Medical Journal in the realm of medicine has a good series on how to report statistics. There's always a book that I really enjoy, always from BMJ, which is How to Report Statistics in Medicine. Very good book, highly recommended. In addition to that, if you are reporting specific studies, I just want to take a second to show you this website. I also showed it to your colleagues. So nowadays, everything is going a little bit in the direction to make things more transparent. For good reason, right? It's open data, open science, transparency. Basically, you want things very structured, very transparent, very easy to digest. So there's the so-called equator network. It's an acronym for enhancing the quality and transparency of health research. Reason why this is so important, because each study design that you may come across, or that you may be writing, or that you may be reviewing a paper, is essentially following some certain principles and should have some specific information shown. And the Equator Network basically provides guidelines for each of these study types. And whenever you, I don't know, those of you that further the research career in some direction, you may review papers at one point. I would start off with downloading one of these guidelines and go step by step through each of these bullet points. So basically, when I write a paper and I submit a paper, I go through these guidelines and I literally make sure I have each of these points addressed. And I would even create a statement adding this and accompanying my submission with it. So basically, it has like very general aspects that are relevant for each part of your submission of your paper. And yeah, so basically it covers an introduction, the methods part, it covers the results, and then moves towards a discussion and a conclusion. So this is a general outline of how papers are being structured. So this is just a little bit of that. So reporting statistics. So basically, we talked already now about the stroke guidelines. So basically, you have the core part, statistics related, is methods and results. Methods is basically where you indicate things like, was my study pre-registered, and if so, where, and what is the number of this pre-registered? How was it planned, and why did you design it that way? What is the data analysis plan? How did you plan to analyze your data, and how did you approach it? Which statistics have you considered most relevant? And then in the results section, you move forward and you describe the analysis in detail. And you show findings from traditional hypothesis testings as well as new statistics. What does that mean? So you're pre-registering your data. Yeah, so traditional findings and new statistics, we talked about this. Traditional findings, you give a difference, you give a little bit of a variability, standard deviation of the difference. And you're saying, okay, so this is statistically significant with a p-value of 0.02%. And we are concluding based on that there's a difference between group A and group B. So that is obviously not enough. And new statistics are basically pushing towards include effect sizes as well as include more detailed information on variability, where most specifically the confidence interval needs to be kept in mind. And in this context, we also discussed the new statistics, if you remember. So, but in the methods, you're putting the pre-registration, you present a power analysis, you show the data analysis plan. Also, how you approached outliers, because excluding outliers is rocket science by its own right. So you need to have a very strong justification why you excluded individual points that didn't really fit your hypothesis. So you need to really have a good argument to have a statistical reviewer pass that. And then basically provides data for each scale that you use, for each questionnaire, for each tool that you used, provides data on reliability and validity that mainly will involve references. References of colleagues of yours that have used this particular questionnaire tool and have basically shown that this tool was sufficiently reliable and sufficiently valid for the purpose you're intending to use it. So then the reporting is done by following hypothesis and tests. You will also need to report the assumptions. Then you report the traditional findings as well as the new statistics. We just talked about that. Make sure that you have plenty of graphs in your paper, because graphs make things just much nicer to interpret. They're always appreciated by everybody reading a paper because it gives a very quick impression of what you actually found. So this is, remember this is a sort of Venn diagram. It basically means you have two independent populations. So travelers that have used Airbnb and travelers that have not used Airbnb. And they have certain preferences for the use Airbnb, what's important to them when they go on vacation. But however, so there are some that are specific to those travelers that have never used Airbnb, and there are some that are specific to those that have used Airbnb, and then there are some that are intersecting. And a Venn diagram is actually a very nice tool to show data of that kind in a very aggregate and very nice and comprehensive way. And yeah, I'm just blown away by staff behavior in Airbnb. I don't know, I've never been in the Airbnb with staff. Okay, but this is basically what you, how you could depict this data. And in the end of the day, with a Venn diagram, you could show these intersections actually, and you could present them in a way that they were representing the percentages of agreement, for example, or the population that have agreed to this particular aspect. But there are various ways how you can approach it. So Venn diagram. Open data practices. So pre-registration, we talked about it. I showed you clinicaltrials.gov when we talked about it. Open data. More and more journals are asking actually for data that have been analyzed and reported in a publication to be submitted to the journal and being made accessible to the reader. So that is, in many journals do request that. So you actually have quite a remarkable number of papers there where you actually can just click and download the data from the website. In some cases, you cannot provide this data freely, and then you would essentially have to request it from the author. But there are different levels. Either you have it to download, or you can request it, or you can request additional analyses, or you just contact the author to ask them to do this analysis for you, or give you more insight into their data. Open materials cover things like, I will provide to you the codes that I have used to analyze my data. Again, many journals, if you publish more complex papers where, for example, you present a mathematical model and you are doing computations based on that model, some journals may require for you to actually upload your codes and to make your codes publicly accessible. So that's kind of covered under open material. Yeah, that's pretty much it. Any questions on chapter 18? I think it's a nice chapter, and it kind of nicely concludes the semester. That's why I like that chapter. Okay, if not, then I would have just gone back. Are there any specific chapters you want to chat about? We have 20 minutes. 6:05? No, 30 minutes, 34 minutes. Any specific chapters you want to chat about? Otherwise, I would just start with chapter 1. Yep.
Oh, actually, then you just start with chapter.
Okay. If you have a specific chapter, I'd be happy to talk about that one. I just thought that the second half of the semester we basically were dedicated to the more complicated topics. And I think you're quite solid now after 2 quizzes. I just want to go back to the earlier things that you don't forget those because that's been quite a while, right? Okay, so chapter 1 would be the one I would start with at this point. And that was really the introduction to statistics part. So we talked about descriptive statistics and inferential statistics. And please don't confuse them. So basically descriptive statistics just means to organize, summarize, aggregate them in a way that makes it more digestible. And that is done in the form of chapter 2, frequency tables, frequency distributions, and as we have discussed in visual displays of data, then in the form of histograms or dot plots or bar charts. Inferential statistics is basically where you use data from samples to essentially draw inferences. So you basically use them for decision making. You basically find out whether there is a difference from before to after. If you send a group of students to get very targeted and tailored tutoring, will their second exam be better than the first one? Things like that. Basically, so these are decisions that you will derive from inferential statistics. You can also use descriptive statistics for inferential statistics, and this is often done in form of graphs, for example, with a little bit of variability estimates in the picture. Know the difference between population and samples. Know that sample statistics are mean and standard deviation, X bars, whereas population mean and standard deviation is mu and sigma. Make sure that you recognize them and don't confuse them. So the sample results are basically strictly sample results are basically used to extrapolate them to populations, assuming that they are generalizable to the population, which is in many cases not true, but hypothetically should be generalizable and extrapolatable. Know the difference between discrete or categorical variables and continuous variables. Group test we talked about. Know the difference between categorical and continuous. Interval ratio. Remember the cookies. Nominal is the name of the cookie. Ordinal is which one is my favorite cookie. Interval is the temperature of the cookie. 0 just being a random number on all possible numbers, whereas ratio has a meaningful 0, right? So how many cookies are left, and interval is what is the temperature of the cookies. So when it comes to the Stroop test, it needs to be ratio because essentially it has a meaningful 0. Can't go negative with time. So also keep in mind here, when you have continuous data, you can make continuous data discrete. You can discretize it. That means you can, for example, you can bin it in certain bins and then just basically categorize each individual data entry in a certain bin. So you make bin 1, 2, 3, 4, 5, and you can then drop the individual data entry in the respective bin and relabel them. The other way around is difficult because you have lost this information. If you only have the bins the individual was in, you can't bring them back to the individual level. So you have lost the granularity, data granularity. Know the difference between independent, dependent, and confounding variables. Dependent is the outcome, is basically determined by the independent variable. Confounder is a variable that is kind of that variable that affects them both or associates with both. And think of ice cream consumption and death by drowning. And the third variable of ambient temperature, for example. That kind of illustrates it nicely. You need for research, you need a reliable and valid measure. That means reliable, it needs to be on day 0, and you measure again 2 days later, it still needs to measure the same thing, with the same level of accuracy. If you measure your height on Sunday and you suddenly I don't know, 10 centimeters shorter than you were 2 weeks before, that's non-reliable measure for whatever shape and reason. A valid measure is if it really measures accurately, and that means if you compare it to a different tool, it will give you the same value, or a reference method. Okay, so good variables and good measures need to be reliable and valid for obvious reason, which is a problem. Hypothesis testing is basically drawing conclusions whether a relation between variables, dependent and independent, is supported by the evidence. So that's where we're getting into hypothesis testing. For hypothesis testing, you need to have operational definitions of your variables. If you're interested in a relationship between the level of happiness of population and the independent variable of pet ownership, the operationalized variable of the conceptual variable of pet ownership becomes, does that individual have a pet or not? So that becomes the level of independent variable. And the dependent variable is happiness. Correlation, we've talked about experiments. An experimental study as compared to an observational study is a study where I have posed an intervention on a population and compared to another population, that sample population that does not have or is not subject to this intervention. So that would be an experiment, and then you see the change in the intervention sample, and you compare it to the control sample, and by interpreting these changes and testing for these changes, you basically will see whether that independent variable, that intervention, actually had an effect or not. So why do you want to randomly assign that? Because if you have differences, if you, for example, you have self-selected individuals into your groups, you will have a disbalance between employees with a health-seeking behavior compared to those that are very unhealthy. So this disbalance creates a disbalance in confounding variables. Only randomization in either of these two groups will essentially allow those confounding variables to be balanced between the two groups. And that will basically give you the true effect of your intervention. If you have confounding in your group allocation, you will basically end up with seeing null difference, which would waste a lot of tax dollar monies, tax money, if you got funding. So randomization is really super important. So you have between groups design and within groups design. We know that data ethics and science, we have that too. Data-related problems, replication failures. Replication is the most important thing, particularly when you do observational research. There are 11 criteria that would allow you to hypothesize causality in observational analyses. Usually causality cannot be established in correlational or retrospective research or observational research because of confounding. And the only way how you can get closer to establishing causality is with the 11 criteria posed by Bradford Hill in the 1970s that basically allow for getting a little bit more convinced of causality or possible causality. Replication is one of them. Replication is one of the most important of one of them, essentially, because if you're repeating a survey in a different population a week later, and it shows you an entirely different result, then there's something off. Either your research wasn't good, either your data collection wasn't good, which is point number 2, or you use the wrong statistics, point number 3, or your tool is not good and doesn't have internal consistency. So, or it was just underpowered and you just were unlucky to meet the wrong random sample and the wrong people. So essentially, so there are data-related problems, there are research and design-related problems with psychological science, but that's true for all science disciplines, essentially. So pre-registration is important because with pre-registration, you minimize the risk of parking, which is hypothesizing after the research results are known, aka fishing expeditions. So basically you have data and you're looking for something that does somewhat associate with each other, and then you formulate your research hypothesis following your association. You shouldn't do that. Any questions? I think it's considerably simple. So then we would go to chapter 2, and that shouldn't take us that long. I think we got that quite well covered. So this is where we talked about volcanoes. So basically, this is where we're now getting into descriptive statistics. You want to describe data, you want to aggregate data, and you want to collapse data down to a very digestible format. One way to do that is with a frequency table, a grouped frequency table in a less granular format, or with a frequency histogram. So, and this is where the distinction starts, because you have one individual raw score, and then you have a frequency distribution. The raw score is one entry. And if you have one entry, then you have 100 entries. And now you want to basically see a pattern or distribution of these 100 entries. So you are describing that pattern by using terms that describe that distribution. So frequency table is a numerically tabular depiction of data. Basically, this is the volcano example. So you basically take the actually characteristic and you're counting each of those entries where this characteristics applies to. So here was volcanoes, then we calculated percentages, then we grouped it, and we took bins of volcano presence in the country, and we ended up with this grouped frequency table, and then we depicted, I think we did right, we depicted it as a histogram. So that's a histogram. Basically, it's a bar graph that characterizes according to bins or individual entries, the occurrence of each individual entry or those entries within those bins as a frequency on the y-axis. And basically, it's one elegant way to show exactly that frequency distribution or pattern of data distribution. You can also then basically overlay this with a frequency polygon or frequency density plot, which is basically this. It's a mathematical function fitting through that data, showing the data basically the smooth spline-like function, allowing for you to see the true distribution of the data. So data we know can be normal, which is symmetric, as we know, or it can be skewed, where basically you have a tail pointing in one direction. So it can be negatively skewed when the tail points towards left, or it can be positively skewed where it points towards right. Dot plots is basically a depiction of one scale variable, basically showing the frequency of each occurring value with one individual point. It's not the most common graph. So visual display, the visual display is a kind of flag because you will quite likely have graphs to look at, to interpret, to extract some information from. So I'm just flagging this. So know the lies that can happen, bias, sneaky sample lie, interpolation, extrapolation, know how to distinguish those, inaccurate values lie. Talked about this. Know scatter plots, know how to interpret them in terms of linear, nonlinear relationships. Know that before you do any correlation and analysis, regression or correlation or regression, always start with scatter plot. Just like visually looking at, is there a relationship? If there's a relationship, how does it look like? And if it's nonlinear, then maybe don't opt for a Pearson correlation coefficient. So know the distinction between linear and nonlinear relationships. Know how to read them. So basically, you have here know how to read them and see the pattern of association here. know how to interpret regression equation, clearly. Linear, nonlinear, line graphs. Line graphs are only used when you have on the x-axis time, and only then you would connect the dots. Never connect any dots on a scatter plot. So a line graph really is exclusively visualizing changes over time. And this is a good example of a line graph. So that's something like this. That's a line graph or a time series plot. This is the line of best fit. Know what the line of best fit is and know why it is fit and how it is fit. Know that it is fit to an extent to minimize the distance between the individual data point, the observed data point, and the predicted data point on the actual fit line. The so-called residual. It means to minimize the distance between those 2 points, and it does that by basically seeking the least square method. So it kind of it finds that way through the scatter by building the least square, least sum of square. That is. Know the difference between the total error, which is the sum of squares, or if you predict the individual data point, the y hat, as mean of y, that is the total error. That's the sum of squares. That's the same sum of squares that we use to calculate the variance in the standard deviation. That is the total error. If you have a residual error, which is, and remember that regression spreadsheet, this is the prediction of the regression equation minus the actually observed points. That is your residual error. That is the distance from here to here for all of these points added up. That's the leftover error. But you need to subtract this leftover error from the total error, which is the first one from the variance calculation. And that gives you that difference of what had been explained by you taking the line and fitting it through that scatter. And that gain in relationship as a proportion of the overall error is your R squared. Please keep that in mind. I'm just emphasizing this after review of the quizzes. Okay, time series plot, bar graph, Pareto chart, bar graph, standard bar graph. You basically see percentage of internet used for them. You see a Pareto chart that basically has the bars ordered, and that's about it. So bar graphs are very elegant to show counts and percentages. And yeah, also the means. Differences between average percentages. You can deceive with the scale. Always make sure that you interpret and look at the y-axis and know if it's discontinued or not. And yeah, choose clarity over cleverness. It's like this is just absolutely unacceptable. Don't use pie charts, please. So this is another known with this opinion. That's just me. It's just, it doesn't give you a good overview. It's just the bar chart will always beat the pie chart. It's like I have never seen a pie chart that really convinced me a pie chart is really a useful way of depicting data. But yeah. Well, different opinions are important. One scale variables you depict with a histogram or a frequency polygon. So you basically just want to understand the frequency distribution. If you have scale independent variable and one scale dependent variable, so scale, that's a scalar graph. But if the independent variable is time, then you use a bar graph, a line graph for time series plot. If you have a nominal or ordinal independent variable, use a bar graph or a Pareto chart, which we have done with our paper cup example, if you remember, right? And if you have two or more nominal or ordinal independent variables and one interval dependent variable, you use a bar graph. So how to read a graph? Well, it's kind of logic, right? So first, you really need to understand the variables. You need to understand which one is the dependent variable, which one is the independent variable. Yeah. You need to understand the nature of both. You need to understand what is the aim of the researcher. Why did the researcher show this graph? And then the rest should go fairly simply. You need to understand what are the units, what are the relationships, is there a line of best fit, what does the line of best fit basically show, what are the levers for, if they're categorically independent variables, what are the levers. So basically you just need to dissect it following a certain outline, and these are the critical questions essentially, how to read and interpret that graph. Guidelines, well, you can review those. More evaporation grids and ducts, don't do graphs like that, and know the advanced future graphing possibilities. There are really cool systems out there. So those of you that are interested in making graphs, is like playing around with these geographic information systems. It was a lot of fun. I did a class on that when I did my master. It was really impressive. And a lot of publicly accessible information. As open source software, publicly accessible information, you can build a map, you can build maps of wherever you're interested in. You can find out publicly accessible information. I did it for access to clean water for some nonprofit endeavor I'm involved in. So it's quite impressive what data you can find. Multivariable graph, so basically you have several dimensions on there. Bubble graphs is one. You all have seen Hans Rosling using his bubble graphs. He's really promoted them strongly. Bubble graphs is one way, contour plots are others. So there are various ways how to build multivariable graphs with a lot of information contained. In case there's a possibility, always choose the depiction method that allow you to also keep the actual distribution, the actual individual data point. Because losing this information of the individual data point, it's concealing information, right? And you're losing information that would otherwise not be accessible to the reader. Then you have a violin plot, which is getting increasingly popular now these days, which basically contains the information of distribution, as well as the information you would have in the box whisker plot, where you have your median, you have the upper part with 50%, the lower 50%, but you have various additional information involved in a violin plot. Good. We have 10 more minutes. Yeah. We have here central tendency. You know mean, median. Please keep in mind that you know that the mean is the one that is most sensitive to outliers. And if there's data changing, or there's additional outliers in there, the mean will be pulled away earlier. The median stays considerably stable, whereas the mode stays stable for the longest period of time. Know how to arithmetically approach them. And know that you have to distinguish between statistics and parameters. Statistics being m or x bar as compared to mu in the population. Know how to calculate and estimate variability, range, variance, and standard deviation. Range, we've calculated all of this quite abundantly. Know the difference between population and parameter and statistics, where basically you have sigma compared to ST or S, and know how to calculate standard deviation. Then we have sampling and variability. You know the difference between a random sample and a convenient sample. So the trick is, and there were some questions in there, random sampling is virtually never the correct answer, because in random sampling, you would have every member of your population would have an equal chance to be selected there. That would mean that this is like almost accomplishing the impossible. So it's very hard to do. And in 90% of cases, you have convenient samples of easily accessible population or sample populations. So it's mostly always a convenient sample. In case there's a question that asks you that, you will need to give a good justification why it's a convenient sample and the rationale why it's a convenient sample. But it's, to be honest, there are some trick questions in there that will ask you for random sampling, but in many cases, it's a convenient sample, also in real life. Also, I gave you this example that most studies of drug trials are basically conducted in a population that would not be the prime target for actually getting this medication in the first place. So they are actually like 20 years younger than the average Medicare population. So there are definitely problems along these lines. So random samples are almost never used because they're hard to use, virtually impossible to use. The problem you have with convenient samples is generalizability or external validity. You can kind of mitigate the problem with replication in different strata of the population or trying different target samples, but basically it remains a problem. Random selection, probability, and personal biases, that's simple. Probability, know how to calculate probability, at least in simple terms. Simple examples won't be anything too complicated. Differential statistics, null hypothesis, projection, null hypothesis. We know all of this, know the difference between type 1 and type 2 error and know how to recognize it. Because that's quite important. So type 1 error is when you reject something that you shouldn't have rejected. Type 2 error is when you're not rejecting what you should have rejected. Type 1 error is caused by subsets, stratification that shouldn't be stratified, sometimes exclusion of some certain strata, various reasons, methods that were not appropriately chosen. Whereas the type 2 error is most commonly caused by the absence of a power calculation, not a large enough sample size, or too much variability in the data for some poorly understood reason. Yep. What's this? And then STAT scores. And I guess this is where we also conclude. So I hope you all remember the STAT score and make sure that you kind of remember the concepts of that, because there may be some question in there that asks you to calculate STAT score, and it's simple as could be. And it's the foundation, but know that you can calculate each number above and below the mean, and you can locate it according to the STAT score, the calculated STAT score, and you're calculating this calculated STAT score as in relationship to the mean, expressed as the number of standard deviation that individual X is located away from the mean. If you look at the formula, if the X is larger than the mu, this has to be a positive set, because that's when the numerator becomes positive. If the X is smaller, then you're subtracting a number that is larger, that becomes a negative numerator, becomes a negative set. Easy, right? So it is then easily possible to calculate backwards by multiplying that set with sigma and adding the mean. And then you get the individual data point back. And if you're being asked to do that by calculating, I don't know, an estimate based on, so let's say you have a correlation coefficient given, and you're asked to calculate the intercept of a regression equation, I guess that's considerably easy then to do, right? If you only have the correlation coefficient, you can also do that if you know standard deviation. So all of this can be considerably easy calculated, and expect questions of that kind. So this is where it's kind of intertwined. That's why I'm included all the chapters. Okay, so this is really to compare apples with oranges because you can now compare with set scores, and this is the beauty of it. You can compare two things that are normally not related, but basically taking the population distribution and relating the population distribution of different variables, different parameters, different measures to each other by relating the dynamics and trends in the population rather than the individual measure. So that's here emotions over time in prevalence on terms of the set scores. So these have changed concomitantly, although all three of them are entirely different. Yeah, set score tell you how the value fits. Also make sure that you know is we have within 2 standard deviation away from the mean, above and below the mean, you have 68% of your population. You have +2 and -2, you have 95, and +3 and -3, you have 99% of your population. So that's the empirical rule. Sample means are normally distributed. That's the central limit theorem. So sample means are now basically, so you quantify the standard error of the mean. So you have the standard deviation of the population given. You're quantifying the standard error of the mean, but basically dividing the standard deviation by the square root of the sample size. By doing that, you essentially get the standard error of the mean, and this is an estimate of if you repeatedly draw samples from the very same population of a predetermined size, knowing that standard deviation from the population, this is how much these means of these samples will differ. And this standard error of the mean is basically then your estimate of what is the probability of that sample that I have in front of me now. I have these 25 hypertensive smokers, and I want to know whether their blood pressure is different than that from the population. And I have the standard deviation from the population, and I know I have sampled these 25 smokers, and I want to compare them to the population mean. And based on the standard deviation in the population, I assume that that variability I will see between means is 10. And now I'm looking at my 25 smokers and I want to compare them to the population mean, and I can quantify now the probability that that sample that I have in front of me is actually indeed different from the population based on that variability estimate. That's the concept, and this is where standardization goes hypothesis testing. Make sense? Good. So that's that relationship is the central limit theorem. So this is standard error of the mean divided by equals sigma divided by square root of the mean. Okay. And this is basically where you then go to calculate the set, where you subtract the mean minus the population mean, and you divide it by the standard error of the mean. This gives you the set. And this is where you come into identifying the cheaters that barely made it above the threshold of 1.96. All right, I guess we're at the end. Any questions? If not, then have a nice evening and utilize the last, how much is it, 12 days? Repeat the lectures, go through the calculations, go through the spreadsheets and the slide decks. Read the books, read the respective chapters that you're not comfortable with.
No class on Wednesday.
You're welcome. You're welcome. So in case there are any questions with any of the questions, practice quiz questions, topics, discussion board, in case I'm not responsive, write me an email and I will respond, okay?
Yeah. Thank you.
Any chance you could post a practice quiz for module 18 or chapter 18, whatever we just did?
Yes, I can do that.
Thank you so much.
Yeah, no problem.
All right.